So here is the workflow used for the impeller optimization, where the blade loading parameters are used to generate the blade shape in Turbo Design 1, and then the resulting performance parameters are fed into Turbo Design Optima, which is basically applying MOGA to drive the solution towards the optimum design. And of course, we need to start by specifying the range of variation for the input parameters, which are the stream-wise loading parameters, because they have direct influence on the surface pressure distribution. And whereas by default the ranges are set to plus minus 10% of the baseline values for each parameter, as you can see here, but there is a machine learning based feature in Turbo Design 1 that can provide initial range estimates for these stream-wise loading parameters. And this is because we want to explore a large design space, but also try and avoid infeasible solutions. And then these are the constraints that are used. So we constrain the throat to control the peak efficiency point, and then the overall diffusion ratio is limited to avoid flow separation. The leading edge lean angle and bow ratio directly impact the maximum blade stress, and so they are restricted as well. And one additional constraint is the maximum surface Mach number, which prevents the compressor from entering the transonic regime. And finally, for the optimization objectives, we want to minimize the profile loss and the secondary flow factor in order to maximize the efficiency. So in this way, using these constraints, we ensure that blade integrity is not compromised in the process of improving its aerodynamic performance. So once the optimization run is complete, which is very fast and only takes about 20 minutes or so on a single core machine, we can see all the designs on a scatter plot between the two objectives. In this case, the profile loss on the x-axis and the secondary flow factor on the y-axis. And here we have chosen to see only the feasible designs which respect all of our specified constraints. And the target case, which is the baseline impeller, actually sits here. And then we can choose to see the Pareto front of optimum designs, from which we can analyze any design of interest. And in this case, we select a design which promises a good trade-off between the profile and secondary losses. And so we use this design for further analysis and for comparison with the baseline impeller. And in fact, this is what has changed as a result of the optimization. So the optimizer has decreased the foreloading at the shroud, but still retains the foreloaded distribution, which helps to suppress secondary flows. And for the midspan, you can see that the optimizer recommends slightly less aft-loading for improving the profile loss in this area. And as a result, the optimized impeller blade is clearly looking very different from the baseline as shown here.